Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we're going to be revisiting Gibbs phase rule with a focus this time on chemical reactions. Now, we've defined the degrees of freedom, F, to be the difference between the number of unknown thermodynamic properties minus the number of independent relationships between those properties. So if we let, and in my notation I use pi for the number of phases, C for the number of components. Using the book's notation, I'll use the scripty M for the number of independent reactions. And then we're going to add an R for restrictions. Now, restrictions could be any number of things, but it would be something like, I want to guarantee that the composition of component 2 is exactly twice the composition of component 1 in the liquid phase. Okay, that's an extra restriction. It's an equation that relates these variables. And if you have those, you need to be sure to include those also. So, my number of unknown properties is going to be based on the number of phases times the number of components plus 1. And the number of equations is going to be twice as many as the number of phases minus 1, 2 for each of those, plus the number of components in each phase minus 1, plus the number of chemical reactions, plus any other restrictions. And when you simplify this, you end up with 2 plus the number of components minus the number of phases minus the number of chemical reactions minus any additional restrictions. Now, we've defined most of these other parts earlier, but we just want to now re-examine this. And in particular, I want to take a moment to focus on these independent reactions. So, if we were given a set of chemical reactions that we knew somehow could happen and would create all of the compounds that we observe in our final product, okay? How can we rigorously determine how many of those are independent from each other? Now, I want to have a general technique of how to do this. So what we're going to do is we're going to consider a set of reactions. And then we want to figure out, are they independent, or how many are? So, for instance, here is a set of chemical reactions. So I have first a reaction where water plus carbon monoxide makes CO2 plus hydrogen. Next, I have hydrogen atoms plus water make hydrogen molecules plus hydroxyl groups, okay, OH. And OH plus CO could make CO2 plus H. Now, these are all possible reactions. Do they form an independent set? Well, one thing that I might do is I might look at what happens if I add these. And if I were to do that, what I end up with is H2O plus H plus OH plus CO makes H2 plus OH plus CO2 plus H. So everything on the left sides equals everything on the right sides. And of course, within this, I could cancel these odd ion groups out, and I end up with H2O plus CO makes H2 plus CO2, and this is identical to reaction 1. So combining reactions 2 and 3 gives me reaction 1. So therefore, this last reaction isn't independent of the other two. And in fact, any combination of two of these will get me, or I can combine any two of these to get me the third. Okay? This one is not too hard to see, intuitively how this could happen, but I want to develop a rigorous approach. So the rigorous approach says I'm going to create a matrix of those new i's, the stoichiometric coefficients, okay? And so what I'm going to do is I'm going to write each reaction in a separate row, and I'm going to sort them by compound. So H2O, CO, CO2, H2, I also have H's and OH's. For reaction 1, I have H2O is consumed, CO is consumed, CO2 is created, H2 is created, and H and OH do not appear. For reaction 2, H2O is consumed, CO does not appear, CO2 does not appear, H2 is created, H is consumed, and OH is created. And for reaction 3, I have no hydrogen, CO is consumed, CO2 is formed, H2 does not appear, H is created, and I wanted that to be a positive one, and OH is consumed. So this is my matrix here. These reactions, the number of reactions out of this set that are independent is determined by the rank. Okay, so probably for most of you watching this video, your question now is, wait, the rank of a matrix? How do I figure that out? How is this helpful? So the rank is going to be a mathematical technique that I can use to rearrange this using row manipulations to create an upper row echelon matrix. So what I'm going to be doing is I'm going to be rewriting these things so that for the first row, I'm going to have a 1 in the first position, and then I'll have some other numbers out there. Doesn't matter what happens to the right. Below this first position, everything else needs to have the value 0. Now, wherever the first non-zero is in this row, I'm going to turn that into a 1, and it doesn't matter what happens over here. But these are all just zeros over here. The first non-zero value, I'm going to turn into a 1, and I'm going to make sure that all of these are zeros underneath. And then I'll put a 1 here. And that's the formal way of doing this. Then the rank is the number of rows that are not all zeros when I get it into this upper row echelon form. Okay, so we're going to look at this in our next video lesson on how this can be done. Thank you.